everyone, welcome to COMP251 Data Structure and Algorithms. In this video we are going to talk about a stack. Last week we have talked about list, an abstract data type that keeps a collection of data in an ordered manner, in a linear ordered manner, and it actually gives you access to the data based on a zero-based index. And it allows you to add the data everywhere you want at arbitrary position at the beginning of the list and or at any valid index between the items. So the thing is, list has a complete set of operations. We have implemented all of these, we have discussed about them, but there are many cases that you want an abstract data type that keeps the data in a linear order, but you don't want to give all of these operations. You don't need all of these operations. You don't need to be able to add and remove the items from at arbitrary positions in the list. So the two special cases of a list that restrict the operations that you defined over the abstract data type. One of them is a stack and the other one is queue, that this week we are going to cover them. We will see that both these data structures, although very simple, but has a wide board of applications in computer science, and many important algorithms works with these data structures. That's why I'm going to talk about them this week, and next week I'm going to talk about the applications of these data structures. So the very first data structure that we are going to talk about is ADT stack, abstract data type stack. So in a stack, we restrict the adding and removing the items to the list to just one side of the list. You can actually think about it in this way, that a stack is a list that we are only allowed to add or remove the data to one side of the list. So it actually makes it a stack if you think about it in a bottom-up way, and if you are allowed to add or remove from the top of the list, so it's going to be a stack. It's just like a stack of plates, a stack of book, that if you're going to add or remove something to a stack of books, you are not going to take it from the middle of the stack, right? You would actually take the one on the top, or add something to the top of that. So the set of operations that we will define for these abstract data types are limited to adding an item, which we call it push, removing an item from the top of the stack, which we call it pop, and in that these are the main two operations, but we actually add a couple of more. For example, pick or top, which is not going to add or remove anything from the stack, just tells you that what is on top of the stack. It just returns the item which is on top of the stack. Size, which tells us how many items is in the stack, and you can actually add is empty, checking that if the stack is empty or not. Clear, that just removes everything from the stack, or this kind of methods. But the main methods that are changing those objects, the data inside this abstract data type, are going to be limited to these two operations. Adding to the top of the stack, we call it push, and removing an item from top of the stack, which we call it pop. So if I can actually show it to you graphically, all these three main methods that we have. Pick, or in some actually textbooks it is called top. It doesn't change anything in the stack. It just tells you what is on top of the stack. One thing that you should be careful about the stack is that when you are creating a stack, you cannot see what you can not see that, for example, what is here. The only item which is accessible is going to be the one on top of the stack. That's why we don't have, for example, indexing, like the method get, that you pass an index and it actually tells you that what is at a specific index in a list, right? We don't have the method get. We only have the method top, which tells what is on top of the stack. The method push is going to add an item to the top of the stack, and you can see that after the item has been added, the top, it is here that we need to have a pointer that tells us where is the top of the stack. So the top will be updated and this new item will be the top of the stack. And the last method, pop, it removes an item from the top of the stack and it returns it. So when you are removing an item, of course here top is going to be updated. This indicator, this pointer that we have for the top is going to be updated as well. Just one note about the implementation of these methods is that if we are going to remove or check, remove something from the top of, from the stack which is empty, or if we are going to check what is on top of a stack which is empty, you can just think about it in this way, that it is not possible to remove something from an empty stack, right? Or when the stack is empty, you cannot check the top of the stack. So we would draw an exception for the case that if someone tries to add something from an empty stack, or if someone tries to check what is on top of an empty stack. So this is just something that we are going to actually consider when we are implementing or abstract data type stack. This example just graphically showed that what would happen if we call a couple of these methods. Assume that you have created an empty stack, so there is nothing there. If someone called the push, for example, value 2 to the top of the stack would look like this, right? If you call another push, so the top of the stack is going to be 6. 2 is in the stack, but you don't have access to it right now because it is not on top of the stack. Push 1 will be actually pushed to the top of the stack. If you now call the method pick, you will see that pick returns the value 1, which is the one on top of the stack. If you call the pop remove the value 1 from the top of the stack and it actually returns it to you. So in fact, the content of the stack now is going to be just 6 and 2, and the top of the stack is going to be 6. If you call another push, so 4 will be pushed on top of the stack, 0 pushed on top of the stack. You call pop again, and it's just showing a couple of these methods have been called. A stack, as you can see, a stack is very simple. It's just a restricted form of a list, but it has a lot of applications. A stack and queue, both of them are the main data structures that helps us to implement a computer. So if I wanted to just name a couple of those applications, any parsing algorithms that you write is going to need a stack. I mean, maybe just the very simple parsing algorithm doesn't need a stack, but every parsing algorithms, for example, to parse the markup languages, to parse for example, a compiler does have a stack because it parses the source code that you pass to it. The parsers for all markup languages like HTML, XHTML, XML, JSON, all of these markup languages, they do parse the source code or the file that you pass to them, and all of them need a stack. Next week I'm going to actually show you a couple of interesting applications for the stack, including some algorithms to convert infix to postfix, or for example how the computer actually implement and maintain the method calls it is using a stack. Wherever you have a recursive algorithms and you wanted to convert it to an iterative version, a stack is going to be used to convert it. In graph algorithms, a stack is very useful. In all depth first search is implemented using a stack. If you actually write the depth first traversal of trees, it is using a stack. I can go on and continue and mention the name of plenty of applications for the stack. So now let's have a look at the implementation. I'm going to, as a stack is going to be a restricted form of a list, so we will see that both array and linked list can be good main data structure to implement a stack, and we will see both of these two implementations. One thing that you should keep in mind here is that when we are implementing the or abstract data type using any of these data structures as the core data structure to store the data, we try to get the best time complexity for the methods. So we have already seen that how different methods for adding or removing to the array or linked list has been implemented and what was the time complexity for them. Here, one thing that you should keep in mind is that our goal always is to get the best time complexity for all the operations when we are implementing an abstract data type. And the best time complexity ever is going to be the constant time complexity. Sometimes we can reach to, a method implemented in constant time. Sometimes we can't. For the case of the stack and queue, we will see that it is possible to implement all of those operations in constant time. And so this is our aim, and I'm going to show you how. So the first implementation is going to be array-based implementation. Here we are going to use an array as the core data structure that we keep the data there. So now we have discussed that if we actually add the items in an array, what is going to be the time complexity? Adding an item to arbitrary position in an array is going to be linear, right? But a stack doesn't need to add and remove items to arbitrary positions. A stack actually just needs to add or remove the data from one side of the list of items that you are keeping, right? So that end is going to be either the beginning of the list or the beginning of the array or the end of the array. So the questions that you have to answer here is which side of the array is going to be better to choose as the top of the stack where you are adding or removing an item to the stack. By which side, I don't mean the end of the, so if you have an array of size, for example, 100, I don't mean this side. I mean, actually, for example, if you have n items, the last index, which is going to be n minus 1, this one is going to be the, the end of the, when I'm actually saying the end of the list, here is the end. So the index 0 is going to be the beginning, and here is going to be the end of the list. So which side is going to be better to be chosen as the top of the stack where you are adding or removing to the stack? This is the question that you have answered. So by just reviewing that table of the time complexity we have discussed last week, about what is going to be the time complexity of adding or removing an item from index 0 or from the beginning of an array or from the end of the array, which is going to be index n minus 1 when you have an item, you will see that, of course, adding or removing from the end of the list or the end of the array is going to be more efficient, because here you don't need to shift anything. The only, when you are adding, you need to actually add to this index, right, which is going to be index n. And when you are removing, you have to remove this item and just need to update this indicator and say that, okay, this is going to be the end of the array or the top of the stack. Unlike that, when you are removing or adding from the to the beginning of the array, you have to shift the items to the right or shift the items to the left, so the time complexity is going to be linear. So here the answer is clear. You are going to use the end of the array as the end at the top of the stack. This figure actually shows you what would happen when we add something to the stack, when we are implementing a stack using an array. Basically, whatever items, for example, if you have 4 items in the stack, the top of the stack is going to be the number of items minus 1. So the top of the stack is going to be, for example, here index 3. So here these steps actually just the comment, and these steps showing you that where it was going to be the top of the stack at each of these positions. When you have only one item, the top of the stack was 0, which actually indicating, it's just like an, a pointer, an indicator that shows where is the item at the top of the stack. When you added something, for example 1, the top of the stack is going to be index 1, the top of the stack is going to be index 2, and here the top of the stack is index 3. If you remove something here, so the top of the stack will be just decreased, right? You are removing something and the top of the stack will be the index 2. So the source code for a stack has been posted on Blackboard. Please check it out. I think this one is going to be pretty simple. This is just a restricted form of the list abstract data type that we have discussed. Many of those methods that we had there, like get or remove with index or add with index, all of those methods are gone, and we only have one method for push, one method for pop, and one method for pick. So let me actually show it. The source code, the full source code is available on Blackboard, but I'm going to show you the main 4 methods here: the constructor, push, pop, and pick, and we're going to discuss them here. Okay, for the constructor of the stack, just before talking about the constructor, the only data fields that we need here is going to be an array that's going to keep all the items. This is the core data structure to keep the items, and I just need an integer variable that I'm going to call it top. Remember when we were implementing list, we called it I think num items or size or something like that, but anyway, here we are calling it top. And of course the implementation is going to be a generic implementation, so I am using any type and indicating any type as the type of the items which are going to be stored in the stack, and it has been actually used everywhere. That shows what is the type of items that we are going to keep in the stack. Okay, as the constructor, so what should we do in the constructor? We have to keep, we have to get some space for the array, right? We just have this is just the, we are getting we are actually indicating the name of the array. So we need to take some space for the array, and we have to initialize top. What is going to be the best value as the initial value for top when the stack is created, which means that when the stack is empty? Top is going to tell me where is the what is the index of the value on top of the stack. So logically, when there is nothing in the stack, the best value that I can think of to initialize top is going to be -1. So this is going to be the full implementation. Later on, I will actually show you that how this value of -1 as the initial value of top is going to make the rest of the implementation much easier. And this line that I'm taking some space for the array, because this is generic, again, I'm actually following that formula that I would take an array of type object, and then I will cast it to any type, because I cannot directly take an array of type any type. Okay, so now let's have a look at the methods push, pick and pop. Okay, what I would like to happen is that this is showing the stack before actually I add anything to that. This shows a stack which is empty. I have an array, the value of top is -1, which basically means that there is nothing in the array. Then assume that I will call push 7. So the value 7 will be pushed to the stack. I would expect that 7 should be stored here, right? And not only this, I would expect that top should indicate this index as well. So these are the two changes that I need. Top should be updated. Also, the value 7 should be pushed here. Okay, so where this value has been pushed at index 0. What was the previous value of top? The previous value of top is -1. The new value of top is 0, which is actually exactly in the pointing to where 7 has been stored. Okay, let me show you another example. If you call push again, for example, push 4, what would you expect to happen? 4 should be stored here, right? And top should be updated, and no, the new value of top should be 1, which is exactly where you are putting the value 4. So it actually tells me how should I implement the method push. The method push can be implemented just in one line. You have to do two things, but it is just the syntax of the Java that allows me to do both of them in one line. You have to update top, okay? And the thing is, the new value that you are going to put on top of the stack should be inserted at the index, which the updated value of top. So I put this plus before top, which basically means that the value of top will be updated first, and then the value that you are passing this object will be stored at items index top, which has been updated. So by putting plus this increment operator before top, it will be updated before you store the object at that specific position. So here in this example, it shows you that what would happen if you call push 6 at this situation. What would happen? Top will be updated first, top will be 2, and then the value will be stored there. Okay, so you can see that I have commented out this line here. I just wanted to focus on the main part of the implementation, which is this line. But of course, because here you have an array, the size of the array is fixed, right? So at some point, it is possible that you fill all of the cells in the array and you don't have more space. If that happens, exactly like what we did in the implementation of the list using array based on array, we need to expand the array. We need to get more space, actually create another array of larger size and copy everything there. So this line is basically you have to comment it out, and this is actually available in your source code. You will see that we will double check if the array is full. We will expand. The method expand is very similar to what we have discussed in the implementation of the list. Okay, now let's actually discuss the method pick. The method pick is not going to change anything in the stack, but it needs to return what is on top of the stack. Okay, so this one is going to be pretty simple. just return items index top. One thing that I have to do before actually returning index top is that what would happen if the stack is empty. If the stack is empty, it just means that you cannot check the value in the stack. There is nothing in the stack to check out, right? So you should throw an exception. And by this sanity check, you would actually kind of avoid the issue that would happen if when the stack is empty, top is going to be -1, right? So this code is going to crash with index -1. This is going, you are going to get index out of range, right? So this sanity check is basically going to avoid that issue as well. So the code is going to be just these 3 lines. So one thing that I forgot about the method push to mention was the time complexity. So what is the time complexity of the method pick? Clearly this is going to be O of 1. It doesn't matter how many items that you have in the stack, the amounts of work that you need to do is going to be fixed. How about push? Except that actually issue that if the array is full, what would happen? This case, forget about that. But the rest of the implementation is actually just this line, which is 2 actions, updating top and then putting the item that you want at the index top. So of course this one is also going to be constant. It doesn't matter how many items you have here. Okay, and the last main method that we wanted to discuss here is going to be the method pop, right? So just assume that, for example, I have 3 items in the stack, then someone called the pop. What I would expect to happen, the thing that I would expect is that I would expect the value 6 would remove, right? And the top should be updated to 1, okay? So to be able to do this, I only need to decrease the value of top. One more thing actually that the method pop needs to do is just return that value which was on the top of the stack, right? So but the thing is, I don't need to do anything with this item in the array. What I need to do is just get the value and for example you can store it somewhere and then return it, but instead of doing that I have implemented using in just actually 1 line, again using the method decrement over the index. So here you can see that I put the decrement after the index top. So here what would happen is that items index top will be taken and then the top will be decreased as well. Okay, so it will return the value of 6 and then top will be decreased to 1. It was 2, it will be decreased to 1. So you might actually think that what would happen to this 6 here? I should actually remove it from the array. But you don't need to be worried about this value. By updating the top and decreasing it, I don't need to do anything about this value, although 6 is still in the array, okay? But I'm not seeing it. And if someone called, for example, the method push after this method, 6 will be overwritten and you don't need to be worried about that. You don't need to put, for example, null there or physically remove it. You don't need to do anything about that index. So it will be overwritten later and we will never see it again. Another method, for example, is empty. How we can implement it is empty is going to be a Boolean method which return true or false. Just true if the method is if the stack is empty, and false if it is not. So when the stack is empty, when the value of top is -1, right? So I can actually just write it down in 1 line. If top is negative, it will return true. If top is whatever greater than -1, so actually it's going to be 0 or more than that, it's going to return false, right? You can implement it in actually in this form, clearly, explicitly as if else statement, but if you write it as just one line here, it's going to be exactly the same. So it just actually looks more professional and nicer. Okay, that was it. All of the implementation of the methods in a stack using array was we have actually just discussed it. Actually, I have already talked about the exceptions. I just forgot to mention that just like the method pick, if someone actually tried to remove something from a method, if someone tried to remove something from the stack, we have to avoid that, right? So here again, we are checking that if the size is 0, we throw an exception, and so we are just avoiding any issue here. So this is the implementation of the stack using array. So next I'm going to talk about how we can implement a stack using linked list. Actually, again, I forgot to mention that the time complexity of the method pop is going to be O of 1, right? The only thing that we are doing here is just updating the this pointer top and just returning that element. So it doesn't matter how many items you have in the stack, pop is going to be done in O of 1. Okay, the next implementation that we are going to see is implementing a stack using linked list as the core data structure. Again, here I have two options to actually use it as top: the head of a linked list or the tail of the linked list. Okay, remember we have talked about the time complexity of add first, add last, remove first, remove last, adding or removing from the beginning of the linked list or from the end of the linked list. This table makes it quite simple for us to choose head as the top of the stack. Okay, the indicator, the head of the linked list is going to be a better choice because removing, adding, and accessing to the item here, all of these actually methods can be done in constant time, so this is a very simple choice. The implementation of the stack using linked list is also available on Blackboard. This is again a more simplified form of the implementation of a linked list, list that we have discussed last week. I don't even need to keep track of tail, only head is enough, and I'm calling it top here because it just actually makes it simpler to work on, right? It is a better name. Just top, the only data fields that I need to keep is just keep a reference for top, which is the beginning of the linked list, and keep track of the number of items that we have in the stack. One more thing here to emphasize is that, of course, you need the class for node. So you need that. In addition to that, this is going to be the main class for a stack here. We call it slist stack. As the constructor, we actually just need to initialize top to null, size to 0. The method push is just adding an item at the beginning of the linked list. So this implementation is going to be exactly like at first that we discussed last week. The method pop is going to be removing an item from the beginning of the list again. So the only thing that, remember when we had a linked list, when you are, okay, let me draw this. This is going to be top, and when you are removing an item from the top of the from the beginning of the linked list, what you need to do is that you just need to take this item and return it, right? But before that, top needs to be updated to this link. So the only thing that I'm doing here is that keep the value, this data here, because I'm going to remove it. This is going to be this line, and then top will be updated to top.next, and size will be updated as well, and item will be returned. So in both the method pick and method top, I would actually just do this sanity check at the beginning, that if the stack is empty, so we throw an exception. So that's it. This is the full implementation. I mean, this one's going to be very short and simple. We have already discussed that. So again, this diagram shows graphically what would happen when you are actually creating a stack, and you have a linked list based implementation. If you push 6, so that's going to be 6 is going to be the top of the stack, or that's going to be the first item in the linked list. 1 is going to be pushed, then 7 is pushed, 8 is pushed. If you pop something, so top will be updated and will refer to 7, right? So it was previously 8, and now it will be actually referred to this node. So that's it. This we are done with actually the both implementations for a stack, both array based and linked list based. We have already seen that the time complexity of all of these methods, doesn't matter if you implement it using an array or a linked list, both of them are going to be constant. And that's it. A stack is going to be one of the very efficient data structures, and there are going to be lots of interesting applications for them. A stack also has been implemented in Java Collection API, and in fact, many methods in a stack has been inherited from the vector collection. Basically, a stack is just actually an extension of the vector, if you're familiar with that. And there are, I have actually added these 2 links to the Java Oracle if you wanted this one as a reference, and check out all the methods which are available for the stack in Java Collection API.